for the invitation. It's great to be here at SPICE, first time. So I'm going to talk about some more detailed concepts about spin superfluidity and the possibility of long-range transport in thin-film ferromagnets. And this work has been done by Hans Skarsvåg, who's a PhD student in my group. He's finishing very soon. And Cecilia Holmqvist, who was a postdoc in my group. And she's now a postdoc in Kalmar in Sweden. So the question that I would like to address is, can a thin-film ferromagnet behave like a superfluid? So we have a thin-film ferromagnet, and we put some contacts to the left and right of this ferromagnet, and we'd like to pass some spin current through it, and we'd like to know, is superfluidity an option in this system or not? If this would be the case, it would be great because we could have some new phase coherent spin transport properties of this system to study. We could enable spin transport without significant losses over very long distances. And this low dissipation could provide possibilities for even applications like interconnects, spin logic devices, and maybe non-volatile magnetic memory devices. So, no. Thank you for your attention. No. I'm going to tell you.
So the previous talk we just disregarded.
No. It doesn't make like that. There's a lot of interesting physics here. Question 2. Can we realize spin superfluidity in other geometries involving ferromagnets? Yes, that's possible. So what I'm going to discuss now is, first I'm going to say something about spin superfluidity, and some of this is a repetition of what Jaroslav told, but nevertheless it might be useful for pedagogical purposes. And then I'll go into some experimental suggestions, and I'll give some results about how this behaves. So, spin superfluidity is a concept that you can realize in many different systems, but one of them is ferromagnet insulated thin films, at least in some idealized model. So if the free energy is such that you have an easy plane anisotropy, then the energy of the system consists of only two parts. There is a stiffness part, and there is the anisotropy energy part. And in this case, the way the superfluid properties come about is that you can separate now the variables into component of magnetization along the outer plane axis and the phase, the in-plane phase. So this is like the geometry. No, I should not push. Okay. So you have the outer plane component, that's the density, and then the in-plane component, the phase, that's the phase of this superfluid property. And if you then, as Jaroslav said, if you now write down the hydrodynamic equations, and first of all just skip dissipation, then you'll find that these equations look like dissipation-less transport of spins. And this comes about in the way that the magnetization precesses at a certain precession frequency, and then on top of that there is a gradient, a spatial gradient in the phase from one side of the sample to the other side of the sample, and that's how you can carry this dissipation-less spin current. So it kind of looks like this, that the magnetization precesses all the time in this film, but the phase of this precession varies from one side of the sample to the other side of the sample. That's how we transfer spins. Now, if you compare this to conventional superfluidity, you can carry out the mapping, and the mapping is such that, well, in a conventional superfluid, you have a superfluid density and an order parameter phi, and now in this easy plane ferromagnet, you have an outer plane component mz, that's the density, and you have an in-plane angle phi. So those are the same corresponding variables. You have hydrodynamic equations for this component mz and phi, the same as in a conventional superfluid. You have a spin current that's proportional to the gradient of the phase in both cases. Turns out you have a linear sound-like spectrum of the excitations in both systems as well, and you can also develop stability criteria for these excitations. So you can now think of trying to study these properties in different devices, and this is the one that Jaroslav proposed, that you can now imagine that you inject spins somehow from the left. They flow via superfluidity inside the ferromagnet insulators, and you detect them on the other side by some means. And on top you can get you can introduce the Gilbert damping, and this is the results in the simple limit that the current now only, this is the spin current, and this is the spin inclination. It only depends on the properties of the contacts, because those are these mixing conductances. And it doesn't really depend on any bulk properties in the limit of no dissipation, but if you do have dissipation, there is a conductance or a resistance associated with the bulk properties as well, because you have dissipation of spins. So it's like a superconductor. There is no resistance inside the system. There's only resistance at the interfaces, and the additional degree in the interior is the dissipation because of Gilbert damping. There are also other suggestions of this, utilizing this spin superfluid properties in more non-local geometries, and these are two of them. So, will it work? Not really. So I'm back to this. Why not? There is an essential piece of physics in this ferromagnet insulators, this thin film ferromagnet insulators. There's an essential piece of physics that is crucial for many low energy properties. And that's
already like one comment.
Yep.
Let's be more precise with the sweeping statements, so that people don't get confused.
I'm going to be more precise later.
Yes, yeah, as I already argued also, there are two ways out. One is anti-ferromagnets.
Yes.
And that's kind of clear from the very beginning.
Yeah.
Right. We had a paper right after our papers.
Yeah, I know.
Anti-ferromagnets, and these effects are not even
yep.
there. Two, thermal fluctuations. And what you're going to talk about, I'm not sure if you're including those.
No.
Thermal fluctuations also facilitate.
It could be, but I'm talking about the ferromagnetic insulator film.
So maybe then should narrow down this kind of sweeping statements.
I was just talking about this films. Just make a very simple message first, but I'm going to make it more nuanced, yes. Okay.
It's recorded.
What?
It's recorded.
I know it's recorded. But it was just to get your attention. Okay, so now I'm going to talk about the dipole-dipole interaction. So let's look at the scaling of the different energies in this system. If we now look at the exchange interaction, it scales like the wave vector squared, which is 1 over, you can think of it as 1 over distance squared. However, the dipole-dipole interaction scales like typically like 1 over distance. So it means that for many properties, the dipole-dipole interaction will dominate long-range physics. For instance, and then one should expect that the dipole-dipole interaction might be important for spin superfluidity because it's a long-range phenomena. It happens, it's a very slow variation of this gradient. So what is this dipole-dipole interaction? Well, you can separate it into two terms. You can view it as there's one static component in this dipole-dipole interaction, and then there's a dynamical component. The static component, that's the component which gives rise to the demagnetization field. That gives rise to an easy plane anisotropy in a thin film, ferromagnet, for instance. The dynamical dipole field is a bit more complicated, and that qualitatively changes the low energy dispersions of all the magnons in such ferromagnets. And one should expect then, or at least could guess, that it's important for this concept of spin superfluidity. So now let's look at the low energy spin waves induced by this dipole-dipole interaction. It gives rise to an anisotropic dispersion relation, and these modes are quite well known. If the magnetization is out of plane, you have so-called forward volume magnetostatic spin waves. The dispersion is such that the energy increases with wave vector. But if you have an in-plane magnetic field, then the modes, the dispersion of the modes is different if the wave vector is along the field or if it's perpendicular to the field. You can actually have negative dispersion when the wave vector is along the field, and if it's perpendicular, it's positive dispersion. So there is something qualitative that's changed in the dispersion of these magnet modes. So now, to get to, let's say, to have long-range spin transfer, the two challenges we have to overcome. The first is that there is a decay of the spin signal caused by the Gilbert damping. And in the setup that we saw so far, that decay was proportional to the length of the device. So the longer you made it, the more decay you had. That's one obstacle that we need to overcome. And the second is now this strong dipole-dipole interaction. I'm going to address now both of these. And that's where I'm going to make the answer a bit more nuanced than in the beginning. So we can solve the first challenge, actually, this decay of the spin signal due to Gilbert damping, at least conceptually. So let's imagine now that I have almost the same setup as what Jaroslav had, except that I put the injector and detector on top of the device, which is not really conceptually that different. But what I will do now, I will induce now excitations of these ferromagnet insulators from the left contact, and I'll detect it by the right contact. The difference when I put them on top compared to when I put them on the side is that if I put them on the side, then the contact area will always be proportional to these, the area of this, what's on the side here, and the same here. In that way, the signal, because the output signal depends on the ratio between the area and the volume. So if I put the contact on the side, when I make the device longer, I keep the injection area fixed, but I increase the volume on my device. But if instead, if I put the injector and the detector on the top, I can actually make the device much bigger by just scaling the, if I at the same time scale the injector area and the detector area. In principle, I could then achieve really long range spin transfer properties, because it only depends on the volume versus area. So I could then have spin transport for millimeters if I would be able to send in a substantially large enough spin signal here. So seemingly, we can have extremely long-range spin transport here without any algebraic decay of the spin signal. Now, the second challenge is this dipole-dipole interaction. And we solve this by simply brute force including it in a numerical code, and solving then numerically the spatial time-dependent Landau-Lifshitz-Gilbert equation, and including these top contacts, both the injector and detector, and looking at what comes out. So this is the first device. We have some injector area. We have YIG, which is on top, and then we have the ferromagnet insulator, and we take it out on the other side, and we solve this spatial temporal LLG equation. We used actually two codes. We used mu-max3, and we also used a homemade code just based on some Runge-Kutta method. We calculate now the signal we get out as a function of what spin accumulation we send in, and as a function of the length of the device. So just to give some essence of what goes on, then the left figure now is this first picture of magnetization inside this domain at t equals 0, time equals 0. And this is with the dipole field at t equals to 0. And you can see that because of shape anisotropy, the magnetization will slightly twist at t equal to 0. And then I'll show you what happens as a function of time. So this is now the case without magnetic field, the one to the left as a function of time, and the one to the right is the one with the dipole field as a function of time. Not so easy for you to see, but on top of the fact that there's a twisting on the magnetization, there's another feature, and that feature is that the magnetization here will precess at the same rate in time at any point in space, but this one will sometimes kind of lag a little behind. So the precession is not just like a complete harmonic behavior, and that is important for this spin superfluid properties as well. So now what's the results? If we now plot the output voltage as a function of the input voltage, and we do this now for different system sizes because we would like to know how far can actually these spins go. We do it for, this is for 100 nanometers, 150, 200, 250 nanometers. So this is 250 nanometers as a function of this input spin accumulation voltage. The first feature you see is that there's a threshold, and this is well understood. This is what Yaroslav said. This is because of shape anisotropy, because when you have this square system, we don't only have the in-plane anisotropy, but there's also a slight anisotropy because the magnetization would like to be along the axis of this geometry. So you have to overcome this by having an accumulation outside which is big enough to overcome this anisotropy energy. And this was also studied, I think, in this paper, this anisotropy, that you have to overcome this. Then for intermediate biases, you do have some linear dependence on the what you get out versus what you came in. So this you can call, like, this is some kind of spin superfluidity regime. But then you also get into this, for higher biases, it breaks down again. And this is because of the magnet-magnet interactions, because this long-range interaction starts to come into play. So the system actually breaks down from this picture of just a simple twist. And I'm going to show more of that. Oops, I thought, but I'm not actually, so I'm going to tell it instead. But the trouble is that what you can see is that if you make the system longer, when you make the system longer, the threshold for the pinning due to shape anisotropy becomes bigger because it scales with the volume of the system. So you can see that for a larger system, already at 250 nanometers, this point will continue to move up this lower threshold. At the same time, the upper threshold will be pushed down because it's easier to excite different kinds of textures because of this magnet-magnet interaction, because of long-range dipole-dipole interaction. And you can only have spin superfluidity in between these two thresholds because that's only where you have the linear behavior. But this threshold quickly goes to 0 when the system size becomes of the order already like 400 nanometers or so. So it means that for this system, for a single fin ferromagnet, at least when you're in this square sample regime, it's very hard to see anything, any effect of this spin superfluidity in this this setup. So, yep.
Good question. That must, so this plot must depend on thickness of the ferromagnet, right? Because the dipole effects become relatively less important as you go to thinner. Because the scale is thickness square.
I don't remember now exactly what the thickness was. I think this was rather thin, but I can look it up. I don't remember exactly what.
Progressively become better and thinner.
Yeah, but I think these were rather thin. I don't remember what they were. Maybe 100 nanometers or something, or quite thin, I think. Not the micrometer, yeah. But yeah. I can look it up again.
Also depends on sensitively on MS, obviously. And
yeah, MS.
Materials like jig or whatever.
Yeah, if MS is small, then all.
To be zero, you can actually go to.
Yeah, if MS is small,
Ferromagnets in which it's zero.
they scale down with MS. Yeah.
Or the ferromagnets, of course.
Yeah, yeah. Okay, so now the lower threshold we can actually do something about because that's because of the shape anisotropy. We can go from this rectangle or this quadratic sample to a circular sample, and I'll show results for that. The scaling we can also get rid of actually by scaling the contact, so we can solve these two issues. So this is now same results now, but for a disk instead, to get rid of this lower threshold. So then you see that you get this superfluid behavior already from 0 more or less, if you would manage to make this disk. But you do still have the problems for larger spin accumulations because you get into the regime where this dipole, long-range dipole interaction starts to come into play. Finally, as already alluded to, you can do better. You have to get rid of this long-range dipole interaction. So what you can do, for instance, is to make, if you would make two ferromagnet insulators on top of each other, and if you would have some, let's say, metallic layer, and if they would couple in an antiparallel configuration, you would then partially compensate this long-range dipole interaction. And you can then write down equations how they behave like if you do so. And you will see that it can behave pretty much like a superfluid case, but now with a much weaker dipole interaction because you have cancelled it. And this is now an attempt to do this numerically to actually test, how long can these spins go if you do so, taking into account realistic parameters, which I don't remember exactly on the top of my head what the thicknesses was, but I think it was on the scale of 100 nanometers for each one of these films. I can look it up, and for some realistic coupling parameter. And this is now the output spin accumulation as a function of the input spin accumulation. And here is the same for two specific input voltages as a function of the length of the device for these realistic parameters. And you can see that for low enough biases, you can push these spins pretty far on the scale of microns in the system, in these trilayer systems. And this is for YIG parameters. It's not perfect superfluid because the drop is somewhat larger, but it's still very long-range transport. It means that the dipole interaction doesn't really kill it in this regime. So, conclusion, single thin film ferromagnet does not exhibit long-range superfluid spin transport. The dipole interaction is important, but if you manage ways to reduce this long-range dipole interaction, you can recover very long-range spin transport properties. And these are the findings. Thank you. Are you more happy? Yep.
I mean, I would not say no. Like to some of the questions that you're raising, I would say it's simply different. Things happening, but okay, of course they get modified. But it's not like there's no effect. It's just, of course, dipole interactions kick in and make things somewhat different. But yeah. But okay, sure. That's another perspective and questions.
So my question is, it seems to be a crossover you are kind of discussing between superfluid and some gradual decrease of superfluidity. Doesn't it contradict the concept of superfluidity as a phase and the phase transition?
So I'm not really sure. I mean, I would not, if you look at this trilayer results at long range, like 2 micrometers, I would not call this superfluid anymore, because it's not. If it should be superfluid, the decay should be according to these. It should only be algebraic decay because of Gilbert damping according to these formulas, but it's not. The decay is bigger, so it is some kind of long-range transport, which is probably a significant component of that is some superfluid transport, but there's something on top of it. So I think it's. I wouldn't say it's not superfluid transport, but it's superfluid and considerable amount of something else on as well.
Ilya?
So it's clear that the dipole-dipole interaction destroys superfluidity in the ferromagnet. So my question is it really the long-range interaction in the bulk of the field, or it is the edge effect, right? Because at the edges, you have really a lot of magnetostatic energy because you're trying to rotate magnetization from parallel to the edge to perpendicular to the edge. And that costs a lot of energy, magnetostatic energy, compared to perhaps longer range dipole-dipole interaction inside of the field from two parts of the field inside of your square or circle. So my question is it the edge effect or is that some kind of a bulk effect?
Let's see. I think I need to think a little more about that. What I know is that it comes from the dipole-dipole interaction, but in which picture it comes from the dipole-dipole interaction, I would have to think a bit more about them. And the edges do play a role as well.
In principle, then you can, if it's one or the other, then there is a fix if that's edge effect, right?
Well, we got rid of the shape anisotropy by modifying the geometry of the system.
But still, right? I mean, there is a significant dipole interaction at the edge because the ground state becomes a vortex, significantly large disk, right? So magnetization still wants to point parallel to the edge.
I think it's mainly part of your threshold.
But I think that mostly modifies the threshold, but when you talk about edges, it depends on which picture you are because there will be like magnetic charges at the edges too. So in that picture, I'm not so sure, but that I had to think about. Yeah. Mm-hmm.
Yeah, just because I heard actually some comments before and also in your talk that dipolar interactions destroy superfluidity. And I just want to make a small caveat to that. If you only have dipolar interactions, you actually can create superfluidity. And I will talk about this.
Okay. Without exchange.
Huh?
Without exchange.
Without exchange.
If you do this in a ferromagnet with a compensating point, could you do the statement that you can go through the compensating point that way you kill the dipolar interactions and then you can observe one or the other? You will see effectively different lengths in each of the sides.
Yeah, probably. But the compensating point is the compensating point in equilibrium. Out of equilibrium, there's probably some magnetization, but nevertheless, it's probably small.
Probably much
Yeah.
smaller, but
Yeah.
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 I heard the discussion between you and Jaroslav that it's better to have a thinner film in this case. Is that why is that?
Well, the dipole-dipole effect goes thickness square because it's dipole here interacting with dipole here.
Yeah, but at the same time, if you have a thin film, then your shape is not really ellipsoidal, or is that exactly what you're saying?
I'm not exactly sure.
In the limit of zero thickness, all these effects go away. Just okay, principle, but of course you can go to zero thickness.
No, I'm not so sure because if you look at the spin waves in thin films, you always have this kind of dip. I mean, for realistic numbers, you always have this dip.
But the smaller thickness, like this effect go
away.
Yeah,
so the dip shifts to higher or smaller wave vectors.
But then very, very small thicknesses. For example, like in very thin, coffee bead, granular films, like people never see this, this kind of magnetostatic effects. You have to go to thicker films.
Right, but in YIG they always see that.
Because they're typically thick.
Right, but even I think at 100 nanometers you will still see that.
That's thick.
Yeah. Yeah.
I have another question.
Yeah.
I mean, in superfluidity, there is an effect called S-Fairbank effect, where you rotate a superfluid. The superfluid component doesn't contribute to the moment of inertia. Is there something analogous in the spin systems?
You rotate the superfluid, and then
so the classical moment of inertia is modified by the superfluid. So the superfluid doesn't contribute to the moment of inertia of a rotating superfluid. It's called Hess-Fairbank effect. I think Tony Leggett used to point out this is a real analogy of the Meissner effect in the superfluid. So my question is, in spin superfluidity, can one construct a similar phenomenon?
My guess is conceptually all these phenomena will exist. I mean, like, you know, you can make rings or whatever, but there's a practical realization of that. That's the challenge, I think.
But your real question is, what's the closest analog of Meissner effect?
Yeah, right. Is there a Meissner effect?
Is there a Meissner effect? Yeah. So the simple answer, no. But then, how can you mimic it? Yeah. I think it's an open question.
Yeah, but this would, you know, Meissner effect would distinguish between an ideal conductor and a superconductor. So maybe here it's just an ideal spin conductor, but not a superfluid.
Okay, it's in that sense it is superfluid. It's not because then it's not ideal.
It's not ideal, yeah, but
well, maybe the name is a bit unfortunate. Maybe spin superfluid, quote unquote. I mean, come up with a better name.
I think superfluid here is just that the spin current is driven by the gradient in the phase.
yeah.
So
That's it. Yeah.
That's it. Yeah.
So they can H bar from the habit.
Okay. Let's let the young people first.
So these simulations, were they done for 0 temperature?
Yeah.
And is it known how would temperature change?
Actually, it wasn't really done at 0 temperature because we started out with some, we just put in some random fluctuations to begin with, but that's just to get the simulations going. But essentially at low temperature, yeah.
Like I would imagine if you crank up temperature, probably these lengths will grow higher or some sort of superfluid will be restored.
Maybe.
So you all look at the DC responses. What about AC? And would some of the effects or problems you have now with DC go away? Because you revert, you know, before you actually have this long range forces really quickly.
Yeah. So this question will address actually one of the papers that I mentioned, by Sotake and myself in 2016. It's exactly the idea. Yeah.
No,
Going to AC will mitigate many of these issues.
You mean the pinning, yeah?
No, also the
everything.
But I wonder about the long range,
Yeah.
because that's something slightly different than the pinning.
Yeah, yeah.
Pinning is
Yeah,
one
yeah.
thing, but
Sure.
pinning I think you can get rid of because you
Yeah.
can.
No,
but
the
yeah.
dipole effects, I guess the idea is that because of the argument, we would expect it to be mitigated, but it has not been looked into carefully
Yeah.
for the dipole effects.
So I'm not sure.
So you find that I mean that even in your like starting bad example, there is a regime of bias in which you have superfluidity.
For if the length is not too long, yeah. If it's 300 nanometers or so, yeah.
But I mean, would be just speculate. But imagine that if you induce the superfluidity thermally with a thermal bias.
Yeah.
Would you imagine? I mean, would you know how to somehow change this simulation? And would you imagine that even in like your bad example, if you do it with a thermal bias, there will be maybe in the linear regime a regime in which superfluidity is still present.
Yeah, for around 300 nanometers, I think it still is there.
Okay. Last question.
And actually, question to both of you. Both of you didn't use the term macroscopic quantum state, which in my view essentially it is. And the term macroscopic quantum state helps, in my view, in the discussion because it has many conventional quantum mechanical properties simply due to the interference effects which you have in a macroscopic quantum state.
I think I didn't use that because everything I do is just semi-classical.
Yeah, but it's fine for a macroscopic quantum.
I know, but I just wanted to stay in the semi-classical picture. Yep.
Well, I agree with Arne. It's macroscopic quantum mechanics in exactly the same sense as ordinary ferromagnet is a macroscopic quantum mechanics, not in any more fundamental way.
I think there's an additional component, and that's the phase coherence of a superposition of macroscopically distinct states.
Yes.
And that's very difficult to see at room temperature. For example, if you have the chirality which goes left and the superimposed with a chirality right, and you would try to observe a state like that, that would be a macroscopic quantum state, and that is very difficult.
Yeah. but we do
But
have
not
interference.
excluded, you know.
One could think of interference effects, yeah. But it's all classical interference effects.
I think it's kind of like just Larmor precession. You can do it semi-classical, but you can also do it quantum mechanical. But you end up with the same result.
So let's thank all the speakers.